So today we discuss potential energy. Okay, some concept about potential energy and calculation of potential energy. So, so some mathematical tools. Okay, like calculus, potential energy. Okay, so there is a source charge, capital Q. So bring a test charge from infinite to that point P. Okay, so the test charge small q, the distance is r. The distance is r. There's a vector r. Its electric field in that direction. Okay, so we know what is the electric field. E, that is equal to source charge q over 4 pi epsilon naught r square, and the direction is r cap. Okay, so electric field at point P, and we know that electric field is independent of test charge, so that's why they look like this. Okay, so there is a no test charge here. So now calculate potential at point P, that is equal to q over 4 pi epsilon naught times r. Because electric field is a vector field and electrostatic potential or electric potential are scalar quantities, so that's why vector sign here. Now differentiate with respect to r, the length. Okay, r, so we get q over 4 pi epsilon naught and 1 by r, d of 1 by r, and we know that that is equal to 1 over r square, so q over 4 pi epsilon naught 1 over r square, that is dr. Okay, and that is a scalar quantity. Now dvdr okay, there is equal to minus q over 4 pi epsilon naught r square. Now if I added if I multiplied by r cap in both direct side, left side and right side, multiply by r cap. Now this right side is look like a electric field at point P. Okay, so differences are there is a plus, there is a minus. So we get minus E vector. So we say that, so E vector, the magnitude is the dvdr. So if I say that E magnitude, field magnitude, that is equal to dvdr. Okay, so now we say that it's a dvdr r cap, that is minus electric field vector, and the direction is r cap, so now direction is r cap. Now box that's very important, very important. Okay, suppose a total electric field, so r here the one dimension. If I say that is a three dimensional, x y z, that is a one dimensional. Okay, so just only length r. If that is three dimensional, so there is a x y z component. So total electric field Et, okay, say calculate the Et, total electric field. Okay, so that is equal to potential V dvdr. Okay, so that's a scalar quantity and there's a unit vector r cap. So that's the minus sign, and that r cap is defined as suppose say that is x I cap three dimensional plus y j cap plus z k cap. Okay, So here you see that same cheese. Okay, so dVdr. So dVdr. Okay, so potential at x, y, z. Potential of at x, y, z. Suppose that is E of x, y, z in vector. So Ex, there is a minus sign. Obviously, there is a minus. So Ex. Okay, just only in vector, that is minus, suppose dv, sorry, minus uh, dv dx, and that is I cap, and suppose the ey, y direction electric field, that's the x direction electric field, that is equal to dv dy j cap, and ez minus dv dz, that is k cap. Okay, if these here must be added here, so we get that suppose replaced by the r with x, y, z, so we get del v, partial derivative of del v del x I cap plus del v del y j cap plus del v del z k cap. Okay, so there is a v common. Okay, so del x I cap plus del y j cap plus del z k cap times v common in these three. So that is a called grad. That sign is grad. Is called grad. Okay, is called grad. That is E electric field. That is E equal to minus grad V. Okay, so clear, minus grad V. Grad is, there is the operator, is the operator, or E is equal to minus grad. I'll say that V. Okay, the three-dimensional electric field, the relation between electric field and potential in case of three dimension. Okay, clear the concept. There we discussed this topic in previous class or last lecture. Okay, so I just recall this topic here. Now the new topic we discussed, the parallel plate concept. New concept is that a parallel plate concept. Parallel plate concept. What is parallel plate concept? Suppose these are the two plates, and these two plates is the same potential here. Okay, so that's why these are called equipotential surface. Here that's also equipotential surface. So there is a two equipotential surface, and that one potential surface is called a plate. Okay, so now put some plate. This plate has a minus potential. This plate have minus potential, and this plate have positive potential. Okay, so that is a gap. These two potential is, suppose potential plate is D. So electric field direction, the very important, that is in that direction. In outside that plate, electric field with a zero, or you can say that is a one chance. Suppose that's path directly, or side outside down. Okay, suppose this like this. Okay, so these plate have potential, say that is a V1 potential, that's potential, plate 2 is a V2 potential. That is a red color plate is called equipotential surface, This plate is also called an equipotential surface. You know that. So the potential difference, so that is V1 minus V2. That's the potential difference delta V. V1 minus V2, that is integration of 1 to 2. Integration of 1 to 2 if electric field in that direction. So plus to minus. So suppose bring the testers from these minus V1 plate or 1 plate to 2 plate. So you get E dot dr, E dot dr or d of d. Okay, that's also you can say that is r gap between. Okay, so dr. There is no confusion. The d and that is also equal to r. Okay, that's why d does look like odd. That's why we replace that small d with dr. Okay. Now electric field is a vector field and there is a partial direction. So that means we say that the direction is now in opposite of this. So minus 1 to 2. Okay. So that is r cap dr. Why get minus sign? Because the V2 is the higher potential and V1 be the lower potential. Okay. So bring a charge. Okay. So suppose that is called, suppose the initial potential, that's called a final potential, that is called initial. So get the minus. Okay, so V2 is the higher potential, V2 is the initial potential. Okay, V1 with the initial, V2 is the final. So final with the V2 is the very higher potential, 1 to 2. Okay, electric field direction. So the magnitude is the minus, that's a minus. So r dr, so we know that the unit vector r cap we get 1. So we get that integration minus 1 to 2 dr. So integration of r. So r2 minus r1. So that's called a position vector. Suppose that is a position of uh, displacement of these. Okay, these two are the displacement. So R2 minus R1, that is equal to, suppose D, suppose that is a D or equal to R. So here we get, and another important point is the electric field. So suppose there is a E outside, E obviously there is outside, E outside, E outside. So E dot D. So not here. From E outside. Okay. So there is a E dot D. And the value of E, suppose say that E equal to 10 Newton per Coulomb and D is called suppose 10 centimeter, suppose 0.1 meter. So V now minus E, suppose 10 and that gap is R. Okay, the times 10 and there's a D. D is a 0.1. 0.1 so by 10. So that is 1 volt. If electric field is a suppose 10 Newton per Coulomb and displacement between these two plates is called 0.1 meter or 10 centimeter, you get 1 volt. Okay. Same condition is here like that. If that is suppose another condition is displacement is 1 centimeter. So that is means 1 by 100. So means that is 0.01 meter. 10 suppose 0.01, remove these two times 100. So get 1 by 10 volt and you get minus 0.1 volt. Okay. That's very important. Okay, how to calculate the potential difference between these two plates, potential difference, and the electric field, the related relation between these two. Okay, that's very important. Now we discuss another important concept is a conductor or in charge distribution. Okay, charge distribution in a conductor, the new concept, uh, charge distribution of conductor. How to distribution of charge in conductor? So there is suppose the four possibilities way to distribute a charge. Suppose you consider there is a conductor. Okay. So first consideration is that the assumption is that the charge distributed throughout the conductor. First, charge that distributed throughout the conductor look like this. Throughout the conductor. Outside, inside. Okay. The conductor. First assumption. Second assumption is say that the all charges concentrated at one place. Second assumption say that it's all charges concentrated at one place. Okay. So 1 coulomb, we get suppose the 100 coulomb, and all 100 coulomb are charges are concentrated at that point. Second assumption. Third assumption, all charge are distributed the outer surface of the conductor. Like that is all charge distributed in outer surface of the conductor, like this, the outer surface of the conductor here. And the fourth assumption is that none of the above, all three are wrong. Okay. Now what is the perfect assumption? If you choose the what is the perfect assumption, first what is the wrong we choose the assumption. First we discuss that what the possibility is that all charges distributed throughout the conductor. That is not possible actually. Okay. If I calculate throughout the conductor all charges, so if I get calculate in electric field, that's get a zero. Okay, plus minus as of distance value these increase decrease, so that means electric field is zero. This is actually not distributed in all over the conductor all charges. Okay, first assumption will be the wrong. Second assumption, all charges concentrated at the center. This is a totally wrong. Okay, because that we know that electric field E is 1 over proportional of r square, depending on distance r is the r. So that's been another wrong concept. So these possibility we ignore that, because all charges are constant at a place is totally wrong. Number 3, all charges distributed outer surface of the conductor. Yes, that's the true, because all charges distributed on the outer surface. Okay, suppose I choose an these type of conductor, an arbitrary shape of conductor. Okay, and there is some of thickness. Okay, suppose you choose electric field in that direction. So these four third number assumption. So skip the fourth assumption, because if third assumption is true, so none of these totally false. There is a all positive charge distributed outer surface of the conductor. So electric field we know that is outward direction. Okay. Now choose a Gaussian surface. Say that we choose a Gaussian surface in here. So one important thing is, if that electric field is inward direction, so see that a Gaussian surface, no charge inside that Gaussian surface. If we choose that blue color line is a Gaussian surface, so no charge is enclosed by that Gaussian surface. So electric field is inward or piercing, both are the same actually. Okay. So number of plus, there is a number of minus, the vector field actually, the electric field. So that is a get a resultant is zero. So electric field that is get inside a conductor with a zero. Okay. But in outside, there is present in electric field. E outside. Okay. That is a possible. So inside a conductor, electric field is zero. So with the help of Gauss's law, we know that. So no charge actually enclosed by that Gaussian surface. So no charge enclosed by the Gaussian surface. Okay. So all the charges of the conductor are in the surface of the conductor. Okay. So we know that from Gauss's law, that is E equal to, suppose the surface charge density sigma over epsilon naught. The direction represent that n cap. N cap represent the direction of the electric field. Okay. So we prove that with the help of these concepts. So from Gauss's law, we derive this. From pi, that is equal to, from Gauss's law, we know that charge enclosed, the q charge enclosed by that epsilon naught. So if that Gaussian surface encloses some charge, suppose say that is a charge here, suppose a minus charge, suppose there is a minus charge q or a plus charge q over epsilon naught. Okay, and phi is the flux, and you know the flux is E dot ds vector integration over a closed surface, that is equal to q over epsilon naught, and E and ds, suppose E in that direction, suppose that is a ds, so ds be the same direction, so a dot be ab cos theta, so cos 0 be the 1, so E outside the integration, you get a ds, that is q over epsilon naught. So what is the value of ds? The area, the surface area. So we say that is E times s, q over epsilon naught. So E equal to q over epsilon naught times s. So charge by surface. So we get surface charge density. So E equal to sigma over epsilon naught. And if you used to put a vector notation here, so E, suppose that n cap multiplied by the both sides q sigma, that is called sigma surface charge density over epsilon naught times n cap, and that is a electric field E sigma over epsilon naught times n cap. That the magnitude of the electric field, that is the magnitude of the electric field, and n cap is the direction of the electric field. Okay, so see that in that diagram with E be the 0. Okay, so also sigma be the 0. If E is 0 and sigma be the 0, suppose you know that V equal to minus E ds. So dVds, that is equal to 0. So V integration dV, that is 0 ds. So that is equal to some constant. So we get potential constant. Here the potential constant. Okay. Now the diagram is, now see that if I modify the diagram in same basic or similar way, easiest way actually. Suppose that that is a surface. Okay, that is the inside. Suppose. Okay. Okay. Now we say that there is a positive charge. Say that is there is a or positive charge of that side of the conductor. So electric field in that direction, and sigma greater than 0. Here, suppose that is a negative charge. Here, so electric field is inward direction. But we say that sigma is less than 0. But in that both cases, so electric field is 0 inside that conductor, and sigma also be the 0, and potential be the constant. So in cases, okay. So that's the very important concept here. We see that if there is a Gaussian surface here, if there is a Gaussian surface here, so electric field cross that surface. Okay, if electric field is cross that surface. Okay, so there is a positive that is either negative charge is here, that's the electric field in that direction. So electric also in that direction plus 2, but there is no minus, so not possible here in electric field inside. Okay, so similar case, there is a minus charge, electric field will be the 0. So if I choose any Gaussian surface, so no minus charge here, so then has the no possibility here. So inward and that is the outward be the same, that is a vector term. So you see, this is called electrostatic shielding. So what is the electrostatic shielding? Is the whatever charge and field configuration outside. So outside with a positive or negative or whatever may they choose, at any cavity of a conductor remains shielded. Okay, so there is a boundary or there is a wall or shield from that outside. So there is a no influence electric field inside that shield. Suppose there is a shield here. Suppose that is a shield. Whatever may the electric field in outward direction. Okay, whatever either in that direction, either be the possible, but total enter some number of amount of electric field is a leaving number of electric field both the same. So that is a cancel too. The total electric field will be the 0. So in outside there is a number, whatever you choose can be either positive or negative. The electric field do not affect the inside of the conductor, do not influence the inside of the conductor. Cavity is always be 0. So electric field will be the 0, and this is called electrostatic shielding. So help of is some device, a measuring device or any other safety devices are produced by the outside electric field. Device safety with that outside electric field. Suppose there is a car, take an example, there is a cable car, electric cable car, the car, if the cable, the car is suppose there is a brake and this cable now touch the body of the car, so some person inside the car are safe. Okay, because the charge only distributed in the surface. Okay, now if that person is trying to jump out of the car or they jump out of the cable car, then the person get a electrified, because there is a jumping need a door or say some passing through that the surface, car surface. The car surface are highly electrified, so that's why you get electrified. Okay, and that's a safety device. When you place it inside, when you put it inside in your body, inside the conductor, will be the safe. Okay, but due to the electrostatic shielding. So the definition is important in board exam. So electrostatic shielding. Okay. So whatever charge and field configuration, charge and field configuration in outside any cavity, inside any cavity, cavity means there is a hole, cavity in a conductor, in a conductor means there is a cavity, there is a hole. That's must be important. There is a hole in a conductor, remain shielded from the outside electric field influence. From the okay. The field inside the cavity always 0. So field inside cavity 0 is called electrostatic shielding. Okay. Therefore, that is a safety device, devices, but safety measurable, because no influence the electric field from outside electric field in that inside of the part of the body. Okay, that is a safety. Okay, clear the concept about the electric field and the charge distribution. Okay, and what is the electrostatic shielding. Okay, so today end the class here. Thank you.